Hello, everyone. This is our presentation on tiny darknet image classification acceleration via HLS. My name is Nikhil Matre, and our group consists of Zach Nelson, Zihao Lee, Siddhant Alawat, and I. In our project, we are optimizing the tiny darknet network for image classification. It can take an input image and provides predictions of the image using a model that has been reduced for a resource-constrained environment. Darknet uses a series of convolutional neural network layers to process the input image, perform computation, and feed the next layer with a feature map. The image below shows the common CNN structure used in Darknet. Darknet uses the ImageNet classification for inferencing. This is a pre-trained model that is used within each layer to set the parameters. On the right, you can see our model has 16 convolutional layers used for the inferencing of our test image, which is a robin. So the first step for our implementation was to clean up the code base, which involved removing the many other types of inferencing implementations that existed in the hardware, as well as reducing the number of buffers that were used for the functionality of being able to run up to 128 images at once. The previous designs were requiring multiple gigabytes of memory to be allocated, which was not available on the ARM CPU without the swap file, which we did not have access to. As a part of this initial implementation, we also worked to hardcode the network parameters, including, for example, the size of the average pool layer, as well as define a struct to include only the necessary parameters that were needed for each layer, so that we could run each one individually, choosing in the future if we wanted to run our FPGA or ARM CPU designs. This also involves basically removing out many other functionalities, including being able to backtrack layers for training, as well as all other types of layers that we don't use, allowing this design to even be capable of running on the ARM CPU. For our first hardware implementation, we had to develop a pipeline structure to get data to pass from the ARM CPU onto the Z board to the FPGA using just the 32-bit AXI buses for each direction. To do this, we first converted all our data types from the float that we used on the CPU to a fixed point representation that could fit in the limited ARM storage. This smaller storage had a slight accuracy loss, but served to allow data to be processed in a much higher speed and also allowed for most layers to fit on the boards except 5 and 6. We also, while had to partition our BRAM buffers, which somehow reduced the BRAM usage. The previous designs used 256 BRAMs for this one storage array. The partitioning allowed to go down to 200 and use all of it, which would have otherwise complicated the LUT logic, but also allowed it to fit on the board. For this higher optimization, we also combined all the functions that we needed for the convolutional layer, including the general matrix multiply, as well as the biases, weights, and storage weights in order for it to be a much simpler optimization process. This allowed us for doing things like combining the individual layer loops, which remove the need for intermediate buffers, as well as flattening the loops that are used for the layer parameters. For most of these parameters, including the weights, inputs, and outputs, different layers require a different amount of storage. So we developed a novel architecture where all of our inputs in the C code were stored as one large storage array, which allowed for each layer to utilize different amounts of the storage for each required actual array, meaning that it all can fit on the board and allow for different shape layers to be processed. After our hardware optimization, we increased performance further by pipelining the inner convolution loop. Then we pre-computed the fixed point representations of the weight scales and bias factors and optimized our data communication. So we send 32 bits every time that we utilize the read and write function. Finally, we eliminated the need for an extra output buffer by simultaneously switching over to sending the output as we computed it, so we could save on LUTs and memory utilization. As a result, our team has effectively accelerated image classification on FPGA by optimizing our setup. We reduced the execution time from 211 seconds on the FPGA baseline to under 27 seconds, achieving a 7.85 times speedup. This reduction in processing time brings us closer to achieving a near real-time image processing for practical applications. In terms of hardware efficiency, we not only enhance speed, but also optimize the resource utilization of our LUTs, dropping it from 44 to 37% without significantly reducing the quality of the computation. Additionally, our FPGA accelerated approach beat both the ARM optimized implementation, which took 677 seconds, and the x86 architecture, which took 99 seconds. FPGA accelerated approach highlights the advantage of potential FPGA optimization in process efficiency. Our baseline model, the system identified a robin with a 75.59% confidence level. Other species like the rambling and others also recognized with varying degrees of confidence. With our FPGA accelerated model, the confidence levels have adjusted, showing a 46.93% confidence for the robin, although there has been a noticeable shift in the confidence matrix. It is essential to recognize that the accelerated model still maintains the robin as a top prediction. This is a testament to our robustness of the system, even with the optimizations aimed at enhancing speed. Our model continues to prioritize the accuracy. In conclusion, our project stands as a compelling proof of concept for performing complex image classification and showcasing the potential for broader applications in efficient image processing tasks.